Okay, so we are starting our last unit ever. You can breathe a sigh of release, or a relief, and it's nuclear chemistry. And nuclear chemistry has always been my favorite, topic in chemistry, um, either because it kind of focuses on a lot of superheroes and comic book um, people. There's just a lot of stuff revolving around nuclear radiation, like Spider-Man, Radioactive Spider, the Fantastic Four, Dr. Manhattan from The Watchmen, Captain America. There's just a lot of a lot of science fiction nowadays that revolves around nuclear chemistry and radiation and radioactive materials, because it's kind of our newest branch of chemistry and physics, and so there's just a lot of speculation about what we're actually gonna figure out how to do from it. So what is nuclear chemistry? And so you might be approaching this unit with a lot of preconceptions about what nuclear chemistry is, and it's not really just about atomic bombs, and there's a whole lot more to it. So nuclear chemistry is chemistry involving the study and the manipulation of the nucleus of an atom. So anytime you look at the nucleus or change the nucleus, it's nuclear chemistry. That's why nuclear sounds a lot like the word nucleus. There you go. So before we do that, we have to talk a little bit about reviewing some stuff from atomic structure, the unit that we did back in early October. So remember that when we say an element is a certain element, it's because of the number of protons it carries in the nucleus, and they call that the atomic number. If you look at an atom and it has 10 protons, that makes it neon instantly. I don't care what it looks like. If it has 10 protons, it's neon. Okay, and that's how we define elements, is based on the number of protons. And then remember, the same element can have different atomic masses because they can contain different number of neutrons, and those are called isotopes. Isotopes have the same number of protons but different numbers of neutrons, which make them have different masses, because the mass is the number of protons plus neutrons. So remember symbols. We put the element symbol here, and then we have the mass number and the atomic number on the bottom. So for example, calcium 40, which means the mass is 40, the mass goes up here, and then the atomic number for calcium is 20. Okay, so that's a little bit of review. So this is an example of all of that. Hydrogen, there are 3 isotopes of hydrogen. You have protium, deuterium, and tritium. And again, they all have 1 proton, right? So they all are hydrogen because hydrogen has 1 proton. But deuterium has a neutron, and so it has a total mass of 2, which is why it has deuterium. And then tritium has 3, atomic mass of 3, because it has 3 total things, 1 proton and 2 neutrons. So it has a mass of 3. But they're all hydrogen because they all only have 1 proton. Okay? So what exactly are nuclear reactions? When a reaction is nuclear, it means the nucleus changes, which means the elements are changing. Because if you change the nucleus, often you are changing the elements involved. So that means, in alchemy, you're trying to do a lot of stuff, but what it's famous for is turning lead into gold, and that's changing an element. But nuclear reactions, we actually will or can do something like that. We will change uranium to plutonium, or vice versa, and it has to deal with how you are changing the nucleus of an atom. So normal chemical reactions, remember, we don't change elements, we just rearrange them. If you react water and iron, all they do is rearrange atoms. You don't change elements. You don't change water, hydrogen, oxygen into something completely different like zinc. That doesn't happen. Okay, so nuclear reactions, any reaction which an element in the nucleus changes. So nuclear stability is pretty much states that some atoms are more stable than others. Okay, and this is how people started to figure out that things were radioactive, is because some atoms are more stable and then some atoms decay. And this depends on the neutron to proton ratio. Okay, you want to keep a certain ratio depending on where you are on the periodic table. Okay, so a radioisotope is simply an isotope of an element, right? It has a different number of neutrons that is unstable. And by unstable, I mean it has a kind of funky proton-neutron ratio, okay? And that makes it unstable, and it becomes more stable by emitting radiation. And so emitting radiation helps the atom achieve a better stability or neutron to proton ratio. So like if you have too many neutrons, an example of that would be it could emit radiation and get rid of neutrons, and that will help it become more stable. So a radioisotope is an isotope that is radioactive, basically. Okay, so then what is radiation? Okay, so if a radioisotope is a radioactive isotope, then what is radiation? And the radiation is either a penetrating ray, which is like an energy or electromagnetic wave, and particles emitted by a radioactive source. So all elements with atomic numbers above 83 are radioactive. So number 83 is bismuth. So anything greater than 83 is radioactive. So from actinium on, radon, radium, all of those are radioactive. Hence radon and radium. There's a reason why we named them those. So pretty much the lower half of the periodic table are usually radioactive, which is kind of exciting, also kind of scary. Okay, so that's your kind of intro into radiation, and now what you have to know by Friday is the 3 major types of radiation. Okay, so there's 3 sources of radiation: alpha, beta, and gamma, and you have to know each one, what they are, and how they work. And then on Friday we're going to talk about how to look at equations with them. So radioactive decay occurs when alpha, beta, or gamma particles are released, and it forms lighter and more stable nucleuses, right? The reason why radioactive decay happens is because they're trying to become more stable. It's kind of like a garage sale. You want to clean out house, and so you get rid of all your junk. And that's kind of what radioactive decay is the nucleus is getting rid of what they don't need. So the first one is an alpha particle, okay? And there's a picture. An alpha particle is essentially a helium nucleus because helium has 2 protons and 2 neutrons normally. So an alpha particle is 2 protons and 2 neutrons stuck together. So technically it's a helium nucleus. Okay, so the symbol for an alpha particle, sometimes you will see helium, right? Mass of 4 total particles and 2 protons, or 4 and 2, and then just the symbol alpha, the Greek letter alpha, which is kind of like a little fish thing. A little curly fish A. So alpha particles is like a shooting out little tiny helium chunks. Okay, alpha particles, depending on how much energy they have, they can actually burn you pretty bad. They burn flesh and they're not fun. Okay, so here's an example of a nucleus that is unstable, and so it releases an alpha particle, which means it loses 2 protons and 2 neutrons, and it shoots it out and gets rid of it, okay? And that's alpha radiation right there. Here's another example. Americium-241 is unstable and becomes Neptunium-237 and loses an alpha particle. So you can see that the element changed because it's losing protons, right? So that means the element is now going to change, and it's also losing mass because it lost 4 particles. So that's why the mass goes down 4. Okay. So beta particles are the next one. Beta is a kind of a letter B with a little tail in Greek. So a beta particle is essentially, as this says, yeehaw, a really fast electron. Okay. Remember, electrons are negative charged particles with 0 mass. They are so small that we basically say that they have no mass. So they are formed by decomposition of a neutron. A neutron can break down into a proton and an electron. And so they release the electron and you're left with nothing but the proton. Okay? So the notation is either an electron which has 0 mass and it has a -1 charge, or you can write a beta symbol, 0 and -1. Okay? Because beta and electron is technically the same thing. It just depends on whether you're talking about radiation, then all of a sudden it's a beta particle. But if you're talking about an atom, then all of a sudden you call it an electron. Okay, so here's an example. Again, the element is changing, right? Hydrogen to helium. And then this neutron over here turns into a proton and releases an electron, because a negative and a positive cancel out to be neutral. So there's beta radiation being shot off, an electron. Okay, the last one is gamma, and gamma is famously responsible in the Marvel comic series by creating the Hulk. Bruce Banner was supposed to have created the gamma bomb, and it went wrong, and that made him into a Hulk. So gamma radiation does not turn people into Hulks, it actually just kills them. So sorry to burst your bubble, but it's true. They're very, very high energy electromagnetic waves. Okay, other electromagnetic waves are just things like light, and X-rays are all both electromagnetic waves, but they're very, very high energy, way higher than normal light is. It has no mass, since it's just a wave, no electrical charge, right? And so, oh, too far. So our notation is the Greek letter gamma, which it looks like this, kind of like a little Y, and then 0 and 0, because no charge and no mass, right? But it does have a very high energy, so we'll see later that this is one of the more harmful radiations because it's pure energy. Okay, so here's an example of gamma waves. Gamma is the only one that does not change the element. So helium to helium, nothing changes, right? Because over here you can tell that they're moving, they have high energy, and that makes it unstable, right? So they lose energy in the form of a photon or a gamma particle or a gamma ray. Okay, remember photon is a light particle, and it makes it more stable, and they're not moving as fast. Okay. So this next picture is a diagram. Oh, too much. This next picture is a diagram of how far each radiation will penetrate and hurt you. So alpha particles, so the first thing is paper. Okay, alpha particles are pretty big, you know, compared to the other ones. You can see that alpha is the biggest because it's 4 of them. And alpha will just bounce off paper. Like, you don't need much to block an alpha particle. You can just hold up a sheet of paper and it'll block it, because it's so big that it won't go through paper. It'll just bounce off. Okay, so anything heavier than paper, it's going to bounce off. Beta will go through paper usually, but your hand will usually stop beta, because beta is just a little electron, right? So your hand stops beta usually. Gamma, remember, is really high energy. It goes straight through paper, it will go straight through your hand, it will go straight through water, and it takes, you know, a pretty sizable chunk of concrete. I forget how many feet of concrete you have to have, but it's several feet of concrete before gamma radiation will be absorbed. So if you want to protect yourself from gamma, you better be in like a serious bunker. You know, fallout shelters have to protect you from gamma, because gamma is what's released from an atomic bomb. So yeah, gamma, bad, 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 gamma. Neutrons are pretty bad too, but interesting enough is that they'll go through paper and they'll go through your hand, and anything that goes through your hand is probably not going to be good, right? You don't want it to go through. You want your skin to block it. So neutrons will go through your hand, but the water molecules can absorb neutrons, extra neutrons. So water usually blocks neutrons, and that's why a lot of nuclear power plants use water as a shield. Okay, so again, alpha is the easiest to block, gamma is the hardest to block, and so gamma penetrates the most and alpha the least. Okay, so that's the end of this part, and I put the question mark because is there really ever an end? No, there's not, because we're going to talk more. And we're going to talk about things like Half-Life on Monday. And so I always thought that if I were a video game character, it would be, I forget his name, Dr. something. But anyway, I mean, I figured that if I were ever a physicist well, I mean, I am, but if I were ever like a lab physicist, I would be the one that would, accidentally split a time rift in dimensions and allow a bunch of aliens to come in and destroy the world. So anyway, this is my video game character in real life. See the glasses, the beard. Anyway, Half-Life. We'll talk about that on Monday. All those fun things. So be ready with your notes, and I'll see you then.